over to full screen. What we were talking about the other day was how do you check to see if something really is a root of a polynomial. And we talked about the fact that if you take the number that you're interested in, so if you have a factor, something like x minus k, to determine if that really is a factor, you take the k, and notice when you pick up the k, you do the negative of that value, substitute it into the function, and if you get back 0, what you're working with is a factor or a root. Okay. Remember, roots talk about where does the function hit 0. Where is the y value 0? When you say something like f of x equals 0, recall that f of x really means y. So when you say something like that, you're really asking where is y 0? Now graph-wise, y equals 0 occurs where? Let's see here. If we do, if we do a little graph, hey, here we are. If y is 0, the y value is 0, okay? You're going to be right in the middle, aren't you? You're going to be on the x-axis. So anytime we're looking for roots, anytime we're looking for zeros of functions, we're looking for values of x where the function is on intersecting the x-axis. One of the reasons why these are so interesting is because if you have a function, let's say we have something like, well here, let's take, it's not going to let me erase that. Let's say we have something like x squared plus 4x minus 10 equals 2. If you have something like x squared plus 4 minus 10 equals 2, we could try to factor the left-hand side. And if we factored it into two parts, what we would have is something or other times something or other equals 2. There are an infinite number of solutions to that. Can you think of two numbers that multiply together to give you 2? 1 and 2, 2 and 1. How about 4 and a half? 4 times a half is 2. How about 6 and 3? I'm sorry, 6 and a third. If you take 1/3 and 6, the 6 divided by 3 will give you 2. How about 8? And then the other number is 1/4. There's a lot of numbers that we could come up with that would multiply together to give you 2. What we ultimately want to do is set it up so that it equals 0, because if it equals 0, we know that one of those numbers has to be 0. The only way you get 0 is if one of the two things being multiplied together is, okay, is going to be 0. So the reason we focus on why do we want roots, why do we want it where it hits the x-axis, is because we want to solve for where it's equal to 0, because that's an easier place to solve. Does that make sense to everybody? Okay. So that's why we're even looking at zeros of polynomials or zeros of anything. What's the point of that? I mean, what's so special about those? Those are situations that allow you to set up an equation that's solvable. If you had x minus 3 times x plus 7 equals 2, we would not be able to say that we know that this x minus 3 equals 2. or the x plus 7 equals 2, would we? Please? Yeah, because what we could do is we could actually set this up for a value of x where this might be 8, and this would be a fourth. Is 8 times a fourth 2? Oh yeah, we were just talking about that. And there are an infinite number of different number assignments we could make to the x minus 3 as well as making to the x plus 7. And with each of those infinite number of assignments is a new value of x. So every problem would have infinite solutions. Does that make sense to everybody? On the other hand, if we have a scenario where instead of multiplying together to give you 2, it multiplies to give you 0, this number has to be 0, doesn't it? Or this number has to be 0. One of those has to be 0. Does that make sense? Can't get around it. No other way. One of those has to be 0. Well, that then gives you, well, okay, the x minus 3 has to be 0, or the x plus 7 has to be 0. So what are the numbers that'll work? X equals 3, x equals negative 7. That's what makes 0 so special. Oftentimes I find people come into this class in calculus and they have no idea why we're setting it equal to 0 other than it makes it easier to solve. I don't know, 0 is easier than 1, but just as good as 1. Okay? So there are some very specific reasons why the interest in roots and y equal to 0. Okay, so we talked about some of these things. The blue writing is what we had done on Wednesday. And we just now talked about the fact that if you have a factor, for example, x minus 3 is a factor, then if you plug 3 in, the function will return a value of 0. That works both ways. If I tell you, for example, that f of 7 equals 0, a real fair question is, what is a factor of this polynomial? If f of 7 equals 0, what is a factor? Well, it's going to wind up being this idea going the other direction. So it's going to give us x, the negative of 7, the negative of a positive 7 is going to be a negative 7, and there's the factor. Does that make sense to everybody? So if you know a value of x that returns a y value of 0, that value of x can be worked into a factor for that polynomial. If we know that x minus 7 is a factor, can we then figure out what the polynomial looks like with the x minus 7 factored out of it? How would you do that? Okay. How about if we did something like this? X minus 7 divided into, oh no, maybe this is why we did that stuff. Whatever the polynomial is. If we take the polynomial and divide it by the x minus 7, won't that give us what the rest of the polynomial is without the x minus 7 in it? Does that make sense to everybody? So that's why we learned the long division and also why we learned the synthetic division. So that when we got to this section, we could say, aha, as soon as I know a factor, I can use that to simplify to some extent the rest of the polynomial. I can start to factor the thing out. Okay? If we know the intercepts, like here. It allows us to factor out the polynomial. So if x equals -2 is one of the intercepts, x plus 2 will be a factor. If we know that 1 is an intercept, x minus 1 will be a factor. And, geez, you're on it now, aren't you? This is going to give us x minus 3 is a factor. And if we know that we have those three intercepts, we could figure out what the polynomial is by taking and multiplying those three together. Hey, what's an easy way to get that multiplied out? I mean, without actually doing the multiplication yourself. Calculator? Can you do this on your calculator? Okay, the calculator won't do this. Rats. They have a TI-92 or something like that that does this, but how about there's a website, www.wolframalpha. Is this sounding familiar? .com. And all you need to do is go to that site and type in expand, do the parentheses, the x plus 2, parentheses x minus 1, parentheses x minus 3, and it'll multiply it all out for you. How about that for easy? So there is a way to get this done fairly easily without having to multiply it all out by hand. Make sense? All right. Reminder. Oh yeah, roots can occur either, well, with a polynomial that is a second degree polynomial, if it's a quadratic, in other words, how many roots can it have? Well, the graph could go like that and it would have how many roots? 2. It could go like this and it would have 1. Or it could go like this and it'll have, yeah, how many times does it hit the x-axis? Yeah, none. So be aware that you can come up with a different number of roots. On this cubic here, how many roots does it have? With the roots being where it hits the x-axis, it's only 1, isn't it? Is it possible to get a cubic, here's one for you, with no real roots? Is that possible? A cubic with no real roots? And Logan's over there, nah, I don't think so. How can you confidently say that?
Well, since it has an odd exponent, the legs will always go in opposite directions.
That's right. With the odd exponent, the legs are always going in opposite directions of one another, which means if one's going up, the other one has to be going down, and that's pretty well going to force you into, why is it doing this? For whatever reason, it just threw us out. So if the one leg is going up and the other one is, okay, now it's having all kinds of fun, is going down, you're forced into having a minimum of 1 root. You could also have 3 roots if it came down, went up, and came back down. Does that make sense to everybody? Okay. We also talked about the way it crosses the x-axis or just contacts it, lets you know if it's an even or an odd multiplicity at that point. Okay. We talked about if you've got all the roots, if you know what the zeros are, you can construct a whole series of factors to completely factor it. And we looked at doing one. Is this looking kind of familiar to you from the other day? I want to make sure it makes sense. Okay, here's about where we left off. This stuff can get kind of messy. It can be a lot of work. If you want to find the root of a polynomial, this technique that we looked at the other day with P and Q will help narrow things down from an infinite number of possibilities to maybe a long list, but at least it's not infinitely long. The way that you go about doing this is you take your constant, that's P. You take your leading coefficient, that's Q, and you factor each of them. Once you have them factored, remember you're doing the plus and minus of each of them, you do all combinations of fractions with P in the numerator and Q in the denominator. Now that gives us, in this case, 1, 2, 3, 4, 5, 6, 7. There are 8 numbers that possible there, aren't there? But with the plus minus, it's now up to 16. When you do this, look for duplicates. Okay, see if there's any duplication of numbers, and there isn't any in this list. Sometimes you can shorten a list by saying, oh yeah, we've already got 2 accounted for. Okay. What's a quick way to check these to see if they're really a root or not? Yes, sir. Plug them in. I've got an outlet here. Yeah, when you plug them in, you're exactly right. Yeah, you can go to y1 on your calculator, and I would plug in the 6x to the third minus the 5x squared minus 7x plus 4. Plug that in for y1. Then what do? Go to the table. Okay. Go to table. Does that sound familiar to everybody? Is that working? And then once you get the table for your x values, the table is going to be shaped kind of like this. And you're going to have x, a line, and then y1. You don't need any other functions in there at this time. And you could plug in x equals 1 divided by 6. And you enter it just like that. Down at the bottom of the screen, you can actually enter in fractions, square roots, logs, e to the 3.6, whatever. You can put in any value you want there, and it'll compute it, assign it to x, and then come back with what the x value is, or what the y value is. This makes it really fast to cruise through these. Really fast. So you could plug in x equals 1/6. You could do negative 1/6. Oh, wait a minute. The negative key on your calculator, is it white or is it light gray? It's white. The negative key is white. What's the light gray key? Subtraction. Okay. Yeah, way to go. Be careful. Do not put the subtraction key in there. You'll get an error. Now, the nice thing of having the table in this stuff is, yes, there are 16 numbers there, but how long is it going to take you to go through those 16? You'll do them pretty fast, won't it? And what value are you looking to get back? How do you know if you have something? 0. So, and I'm just making this up. If I put in 1 and it comes back with 0, that means 1 is a 0 or a root of it. That means x minus 1 would then be a factor of it. Does that make sense? 1 is not actually a factor. How do I check it that fast? To know that 1's not a factor. Plug 1 in here into the function, here, and here. So it's going to give you 6 minus 5 minus 7 is a negative 6 plus 4. Negative 6 plus 4 isn't 0, is it? If it was a root, what value would we get back? 0. Okay, so that's a quick way to do it. Okay, so here are some of the values off of that table. What are the roots? What are the roots of this particular function? Yes, sir. 1/2, -1. Good. You're right. How'd you get those? Way to go. Yeah, you just look for the zeros. You go shopping for zeros, and every place you got a 0, whatever the x value is, boom, there is a root. And the cool thing then is we can factor this as x minus 1/2, x plus 1, x minus 4/3, and that gives you part of the polynomial. You're already off and running. Does that make sense to everybody? It makes, yes, sir.
So, when you go back to the other screen, where did you get the numbers from?
These numbers here?
Yeah.
Those come from, the p-values come from taking the 4 in your polynomial, and you take that 4 and you factor it. What are the things they'll divide 4? 1, 2, and 4 will divide into 4. And you do plus or minus because you could do 4 divided by a -2, and that would work. So you do either the positive or negative. Then for the lead coefficient, 6. Ooh, what are numbers that'll divide 6? Well, that would be 1, 2, 3, and 6. And you would do the positive and negative once again because 6 is divisible by -3. Just like it's divisible by +3. Does that help? Yeah, good deal. All right. So we have a polynomial. We found the 3 roots, and we can rewrite it like this. Now, here's something that gets tricky. If you're kind of zoned out or thinking, gosh, it looks sunny and nice out. Okay? Tune back in for a minute. This factor, x minus 4/3, actually says that x equals 4/3, doesn't it? That's what that means. Do you buy that? This can be rewritten as 3x. Maybe it can be rewritten. Geez, it's blowing up. Okay? It can be rewritten, if it'll let us. X minus 4/3 equals 0. If we multiply through by 3, we'll get 3x minus 4 equals 0. This is where that particular factor came from. The x minus 1/2 is going to work in a similar fashion. You have the x minus 1/2 equals 0. Multiply everything through by 2, you get 2x minus 1 equals 0, and aha, here is that term. The whole point of rewriting it like that is so that you don't have a bunch of fractions laying around. It looks prettier. Does that make sense? Okay. Okay. There's an interesting little rule called Descartes' rule of sign change. Descartes, a mathematician, came up with all kinds of amazing stuff. Okay? One of the things that he came up with was you can figure out how many real zeros there are. Okay? The number of positive real zeros is equal to the number of variations in the sign. What is he talking about? If we have something like y equals 6x to the 5th minus 4x to the 4th minus 8x cubed plus 7x squared minus 11x plus 3. You can look at that once you know about this rule of sign change and figure out how many positive real roots the equation has. What you do is you go from here to here. Do you see it? It changed signs. So that would be a sign change. Now, from -4 to -8, did the coefficient change signs? No, that doesn't count. From -8 to +7, is that a sign change? Yep, that counts. From 7 to -11, is that a sign change? Yes, that counts. From -11 to 3, is that a sign change? Yes. So how many sign changes total did we have in this particular polynomial? See if there are 4 of them? So that tells you that 4 of the roots are going to be positive values. Make sense? Please? I counted up the number of times we changed from a positive to a negative or from a negative to a positive. How many times it changed signs? Yeah. Yeah, and then from the -4x to the 4th to the -8x cubed, there wasn't any sign change, so it didn't get a little check mark, it didn't count. Okay, so that's the way you figure out the number of positive roots. Now remember, what we're working with here as we move through this section is what are some different ways to spot roots? What are some ways to test a root? This is going to tell you, how do I know when I'm done looking? That's a good question. How do I know when to stop? If we found 4 positive roots, could we keep looking? Or should we keep looking? We could, but should we? No. This says there are only 4 of them. Make sense? Now, if it's not 4 of them, it would be 2 of them or 0 of them. It's going to decrease by an even integer. There's some reasons for that. We won't get into it right now. Okay, so that's how you locate the positive roots. How do you figure out how many negative roots this thing might have? Well, what you do is you plug in the -x and you count the number of variations. What? Well, let's say we have something like y equals 6x to the 5th minus 11x to the 4th plus 3x cubed minus 8x squared minus 17x plus 4. Okay, to warm up, how many positive roots will this polynomial have? Yes, sir.
Wouldn't it have negative roots?
It's going to have some negative roots. Right. And we're going to go after that in a minute. But what I'm doing first is backing up and saying, okay, before we get into the new stuff, how many positives would it have? It is going to have some negative ones as well. Okay, Logan's over there saying 4. Here's a sign change, sign change, sign change. Next one, a sign change? Nope, just leave that flat. from here to here is a sign change, 4 of them. Got it. Okay, so that is the previous slide. Now, the new thing that we're getting thrown in on us this time is it says plug in the negative of x. So if this is f of x, we're going to evaluate f at negative x, which is going to give us 6 times negative x to the 5th minus 11 times negative x to the 4th, 3 times negative x cubed, 8 times a negative x squared, minus 17 times a negative x plus 4. Okay, we've got that. Now, let's figure out what that really equals. And the thing to realize here is if negative x is raised to an odd power, will you get a negative x or a positive x back? Okay, so for example, if we have negative x raised to the 3rd power, that's negative x, negative x, negative x, which is going to be what? It's going to be the negative, isn't it? Yeah. Okay, yeah, hold on to that a second. We'll go after that one. So in this first one, it's an odd power, so what we're going to get back is a negative 6x to the 5th. Does that make sense to everybody? Because he has a negative. Now, if it's an even power, if you take this negative x and you raise it to some even power, what do you get back? Positive. So what that's going to tell us here is for this second term, we're going to get back a positive. So we have a negative 11 times positive. Oh, well, that's going to be a negative 11x to the 4th. Does that make sense to everybody? Moving on to the next term. Negative x cubed is going to give us a negative x cubed times 3, which is going to be a minus x cubed. What's the next one going to be? Right. Yeah, because this part will be positive, so the negative is still going to be a negative 8x squared. The negative 17 times negative x is going to give you what? Positive 17x, then a positive 4. That's a little trickier than the other way around, isn't it? The second part you're already good at. How many sign changes occur in that polynomial? From x to the 5th to x to the 4th, same sign or different? There's just going to be one. This is going to be the same, same, same. Oops, this is different. And that's the same. What?
Skip that step?
Skip which step?
Because you found that there were 4 positive answers.
Right.
And only 1 left.
That's right.
So you could skip that.
You could in this case.
But not every
What if there were 2 left? Now this is where things get a little messier. They keep saying the number of negative real zeros. What could be the case is you have 4 that are positive real zeros. Okay? It could be 4 positive real zeros, and the other 2 could be strange things like minus I and plus 4I. They say real zeros because you could also come up with complex or imaginary zeros. However, you will never just get one imaginary root. What always winds up happening is the imaginaries come in piles of 2. They come in groupings of 2. So what you would have here would be x minus I and then x plus I. but it is possible to get a grouping of 2 imaginary roots, but it'll always be in groups of 2, 4, 6, 8. But you're absolutely right. If you've got a 5th degree polynomial and 4 of them are positive, you don't have an option there for negative or for imaginary roots because they come in 2s. You've only got 1 root left. It has to be negative. Good thinking. That's exactly right. Are you okay? Okay, take a look at this one. How many real roots? How many negative roots? Or how many real positive roots and how many real negative roots? Let's see, from this to there is a sign change, isn't it? Ah, rats, that's right, there's a positive 1 there. From here to here is a sign change. From here to here, not a sign change. From here to here, it is a sign change. So it looks like there are how many positive real roots? Okay, it's going to be, here's one of them, here's the second one of them, and there's the third one of them. Because in front of the x to the 4th is a positive. That kind of throws you for a loop. Put that positive in there. Are you okay? Or you still want 2, don't you? Okay, let's back it off to here. First off, we have here a positive 1 for our coefficient. Then we have a negative 6 for our coefficient. A positive 8, a positive 2, a negative 1. We go from positive to negative. That's a change in sign. That's 1. We go from negative 6 to positive 8. That's a change in sign. That's 2. We go from positive 8 to positive 2. Is that a change in sign? No. So we're still at 2. You go from positive 2 to negative 1. So that's a 3. A third sign change. Sneaky? Right, it's saying the sign changes 3 times. Yeah, you want to count how many times you get a sign change. Okay. If you just count the number of positives or just count the number of negatives, that doesn't necessarily yield the same results. For example, suppose you have something like x squared minus 6x plus 7. How many sign changes are there for that polynomial? Well, you go from a positive 1 to a negative 6. There's 1 sign change. You go from a negative 6 to a positive 7. There's a 2. But, watch this. What if we go x squared plus 6x minus 7? Now, how many real positive roots are possible? 1. Because from here to here, that's no change, is it? Goes from positive to positive, no change. But from the 6 to the minus 7, there's a sign change. Now we've only got 1 positive root. Earlier, even though they've got the same numbers, 1, 6, 7, because the signs are different, it'll alter the number of possible real positive roots or real negative roots that you might get. Make sense? Okay, here we go with the negative deal. Is that working for you okay? We've already played around with that some. It allows you to count things up. Hey, look at this. How many times does the sign change on that polynomial? goes from positive to positive, that's no change. Goes from positive to positive, that's no change. So far we have 0. Here it goes from positive to negative. Oh, there's a change. So there's 1. And then we go from this negative 2 to minus 1. Well, that's no change. There's only one negative real root. How'd you notice say negative this time? Because we're using the negative x. Is everybody good? Working? Okay. You can use this factoring stuff for degree 2 or greater. Why can't you use it for degree 1? Why can't you use factoring with a degree 1 polynomial? Well, let's take a look at an example of a degree 1 polynomial. If you wanted the root for that, you would take the 3x minus 12 and set it equal to what? 0. Do you have to do anything in the way of fancy work to get that one solved? Maybe I need to... No. Jeez. It's not showing any changes on your screen, but it just went through several changes on my screen. Okay. If we set this equal to 0, we're almost as good as done here, aren't we? We don't have to factor that out. Move the 12 over, divide by 3, and you can look at it and see that x is 4. Okay? So the degree has to be 2 or bigger. Not only that, but what could you factor out of there? You can factor a 3 out. Yep. But you're not going to factor any x's out, are you? Just numbers. So it's going to stay a first degree polynomial. It's not going to change. The degree isn't going to change. Yeah, you're stuck with it. Or I'm stuck with it. Whoever has it is stuck with it. Somebody's stuck with it. Okay? Here we go. You're given a couple of polynomials. Here's one. Find, this is real fair for next week. Determine all of the real solutions. Oh no. Now the first thing to notice on this one is it's x to the 4th and x squared. This will actually factor. It will? Yeah. Okay. See it? It factors into 4x squared minus 9, x squared plus 1. Hey, before we get into that, how many sign changes does this have? Goes from here to here. Well, wait a minute. If it only has one sign change, how many real positive roots should it have? 1. Okay, so let's keep that in mind. We should only get one real positive root. Okay, so we take this, factor it, and you have this 4x squared minus 9 is 0, or x squared plus 1 is 0. Hey, do you know anything about the x squared plus 1? What's that going to give you in the way of roots? Well, it won't give me any roots, but it'll give me gray hair. If you solve this, x squared plus 1 is 0. That's going to give you x squared equals negative 1. X is equal to plus or minus the square root of negative 1. Uh-oh. X equals plus or minus I. Does that look familiar? Oh, man. That gives us that a couple of the factors are x plus I, x minus I. They come in pairs. Complex conjugates, that means one's the plus, the other's the minus. Complex means there's an I. Conjugate means one's plus, one's minus. Uh-oh, so that's really how many roots there? 2 a minute. Okay, so when we solve this 4x squared minus 9, okay, we're going to wind up with x squared equals 9/4. But when you take the square root, you get 2. X is equal to a positive 3/2. X is equal to a negative 3/2. Well, wait a minute. Earlier, with using Descartes' rule of sign change, Logan said there were going to be how many positive real roots? 1. How many are there? It gives 2 solutions. You're right. But be careful, how many positive real solutions? Yeah, there's 1 positive real solution. How many negative real solutions? You mean this Descartes' rule of sign change really works? It really works. Who would have thought? Well, if the sign changes once, you get 1 positive. Now, to figure out how many negative roots there are, what we would have to do would be to substitute in a negative x. But we didn't do that here because when you raise a negative x to an even power, it's always going to come back x, isn't it? So if we do it to the negative x, we're going to get this back. And we already know how many sign changes there are there. How many are there? 1. So if we put the negative x in, we're going to get that back, and we're only going to get 1 sign change, which means there will be 1 negative real root. And if you take a look at this, whoa, check it out. There's 1 negative, 1 that's positive. So this stuff checks out. How about that one? Tell me about this one. Well, first off, Chuck, I really wouldn't want to have to factor that. You may have not seen anything factor like this in a while. Okay, we have all the powers of x there, don't we? We can, with these first 2, rewrite this as x squared times 2x minus 3. Okay, so what? The second 2 each have a factor of 4 in them. We could factor out the 4. If we factor the 4 out of here, you can get a positive 2x. Factor the 4 out of here, you're going to get a negative 3. Now you have 2 terms, this one and this one, and from each of them you can factor out a 2x minus 3. If you factor the 2x minus 3 out of the first term, you're left with x squared. You factor the 2x minus 3 out of the second term, you're left with minus 4. Is everybody okay so far? Whoa, might have been a while since you've done factoring like that. Might have been like 19 years or so since you've done factoring. Never seen that before, Chuck. Sometimes you can line them up like that. I don't want to do that, Chuck. That doesn't look like much fun. Okay. Once you've got it to the factorization that's there on the right-hand side, and you know it's equal to 0, this is going to give you x equals 3/2. What's this going to give you? What's the x squared minus 4 equals 0 going to give you? Well, let's see, that's going to give me x squared equals 4. X equals the square root of 4. Oh, wait a minute, if I'm doing square root, I need plus or minus. So that's going to give me x equals plus or minus. The square root of 4 is 2. So it gives us a total of 3 roots. Does it shock you that we get 3 roots out of this? Shouldn't. Why didn't it surprise you, Austin? Yeah. Your highest degree is 3, which says you're going to have how many roots? 3. Could be one of them's a real root and 2 of them are complex roots, because complex always comes in pairs. But in this case, let's see, we're going to have 1. It says we're going to have 2 positive roots, aren't we? And if we have 3 total, the other one has to be, as you pointed out earlier, negative. Yeah. Uh-oh, solve the equation graphically. How could you solve this graphically? Well, you put it on the graph. Yeah, and then what? You ask the calculator to locate the coordinates of that root. Do not use trace. Your calculator may have a trace button. It gives you the illusion of being right. It just gets you close. It's like you asked for directions to a specific store in Kenwood Mall. And I just get you to the entrance to the parking lot. Does that get you to the specific store? You've still got a lot of looking to do, don't you? Okay? If you use trace, it just gets you in the general area. It doesn't get you where you need to go. But it gives you the illusion that you're there. It'll give you a number with all kinds of digits after it, but it's not right. Be sure that you go with calculate, not trace. Intermediate value theorem. This is cool. This is pretty straightforward to go after. Let's say that you looked at your speedometer at one point in time and you're doing 20 miles an hour. You looked at your speedometer a little bit later and you're doing 50 miles an hour. Are you fairly confident at some time, even though you weren't looking at your speedometer, are you confident that at some point you were doing 42 miles an hour? Why? You're at 50 now and we were 20 before. That's right. You've got to go through every speed from 20 up to 50. And that's exactly what this says, is if it's continuous, if there are no breaks, and you've got a low value and a high value, the function will take on every value in between those. Guaranteed. So if you have a function that goes like this, and we've got a high value here, let's say this is the point, come on and write, 1, 7, and this is the point 4, -6. At some point along this graph, does it have a y value of 0? It has to, because if it went from a height of 7 to a low point of -6, if you're going from 7 to -6, don't you have to hit 0 somewhere? Okay. That's what the intermediate value theorem tells you. That thing is pretty cool. Okay? Gosh, I guess we'll just have to deal with this later. Oh, here's one on mileage. There you go. Whoa, guess what? John's smiling back there. It's time to go. That may be what he's smiling about. But you've got all the information done now for section 4.4, and the homework's already up. No, Chuck, not that. Hey, I'll see you all next Monday.